We are in the branch instructions, and last time we look at this problem if-then statement. So if I equals to j, we add g and h. If they are not equal, we subtract f minus i. You will be given register for R1, use variable f, R1 as a g, R2 as a h, R3 as a i, R4 as a j. So first thing we want to do, we want to compare I and j, which is R3 and R4. Basically, we are subtracting R3 minus R4. If they are not equal, that means we need to go 1 and subtract. If they are equal, we're going to add. And we can also use BEQ, then it's going to be different sequence. This is not done because we don't want to execute this guy after we add this. This is the subtraction is for when these I and j's are not the same. So since they're the same, we want to add, then we don't want to subtract again. Therefore, we're going to skip this line. How? Unconditional branching, which is BAL. Once you hit this, no question asked, right? Just jump it into go to. That's what we did last time. Any questions? Also, we can do for loop. In this C code, we want to add from 1 through 9. So initialize as a sum equals to 0, and then we want to add until the I equals to 10. So R0 equals to I, R1 equals to sum, right? That will be given, and then we're going to go through this iteration. For loop, we're going to compare R0, and that is I. If I equals to 10, then we are done. So we go done and branch, executing some other instructions after this. If it's not, we need to add R0 plus R1 and put it back to R1, but increment by 1. And then we add R0 to 1, so that now R0 equals to 2. And then go to 4, execute this, compare. Now it's 2, so we need to go through, go back. Now R0 is a 3 now, compare. They are not equal yet. Go around until R0 is 10. Once we have R0 is 10, we're done. So we jump to the down to done. From now on, we are going to learn how we actually go from assembly language to machine language. So you need to look at the handout. We're going to look at all those portions for 3 different ones: data processing, memory, and the branch. So the design principle 1, we already talked about it. It regularly supports the design simplicity. And in this architecture, this architecture, we have a 32-bit data, 32-bit instructions. Therefore, everything is a 32-bit. It's easy to decode and encode. So multiple instruction format allow the flexibilities. So meaning sometimes we can have add and subtract. We can have register, 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 or register, register, and any number. So it requires 3 operands. But the LDL STR, we use 2 register and 1 constant. Okay, sometimes we can use 3, but typically for our class, we're going to talk about 2 register plus and the constant. So instruction format. This is the typical instruction format for our ARM architecture. And we have 3 different ones. The first one is a data processing. It's similar. I mean, for source 2, it's going to be 3 different ones, as you can see from handout. And also, funct can be split into this way. It was a 6-bit with the 3 CMD, I, and S. What are they stands for? I is the immediate, S as the set for flags. And then memory, again, 32-bit for the funct this time. Oh yeah, it's really complicated, right? So you need to understand every single bit of these letters. And then branch is the easiest one. And this is the format. Now, as you can see, the 4 most significant bits, they are all COND. So the 4 bits, 31 through 28, they are all COND, 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 COND. And then next 2 bits is opcode. OP stands for opcode. As you can see, opcode for data processing, it's going to be 00, memory, 01, branch, it's going to be 10. And then the rest, it really depends on the instruction. We have to decode it. So we'll get into data processing first, and then we'll get into memory, and then branch. In the data processing, we have this as a general. So specific conditional execution. That is actually from second page of your handout, and conditional execution. Look at the conditional execution. In the data processing, we are talking about AND, OR, comp, all of those. So we don't have really conditions in here, right? So in this case, for the data processing, we're going to use the last one we call 1110. 1110 is always branch, unconditional. If it's not applicable, we're going to use that number. It's called opcode, funct, functional operation to perform, ln, ld, and source. ln, ld. ln is the second or third. ld, that's something you should know. ld is the destination. So any register comes first, we said that is the destination register, right? That should be in here. ln and ld, there are 4 bits. Why? How many registers in our ARM architecture? 16, right? R02, R15, R0 all the way down to R15. That's it. All the registers, we have to use only these. You cannot use anything else. So if you have 16 different registers, how many bits of the binary number required to represent 16 different names? 4. That's why it's 4. So we can fit it 0 to 15. And this funct is now, we can separate into I bit and S bit, and in the middle 4 bits of CMD. And I as a immediate, S as a set for the flag, and CMD. Let's take a look at the your data processing. First page, look at the data processing. If the CMD is 0000, what is it? And, right? Everybody see it? If we have 1010, 1010, compare. And I bit, if I equals to 0, then source 2 is a register. If I equals to 1, then we have to use immediate. I'll tell you more about this. S bit is for the set condition flag. So if you see the S after add, subtract, whatever in the data processing, then S bit is going to be 1. If you don't see S at the end of the instruction, the S equals to 0. Now, 3 different scenarios in the data processing. So you need to figure it out which format. So from 11 to 0, could be the source 2, could be this guy. 11 to 0, 12-bit could be this guy, could be this guy. First thing you want to look at is I bit. If I bit equals to 0, we don't have to have an immediate. I equals to 1 means it's an immediate value. Therefore, we have to have this. So that's straightforward. So we need to look at the I equals to 1, we pick this guy. If I equals to 0, we pick this guy. How do you know I equals to 1 or I equals to 0? Add R1, R2, R3, subtract R4, R5. Let's look at the subtraction first. Subtraction, 1, 2, 3, which one? First one, because that's the immediate. We need to put some immediate value. So the 10 should be in here. There's no immediate for these two. So now, looking at the instruction, you decide which one is the right fit. That's the first step that you need to do. Then we need to figure out the rest, all these numbers. Okay, so we'll get to that. Are we okay? The subtract, the second instruction, we have to have this format, the first one. Now, looks like the first one, add. Add R1, R2, R3. So there's no immediate. So either this or this. Which one? It's the second one? Why? Okay, that's fine. So now we have three different ones. It's called immediate, the first one. Second one is the register. Third one is a register shift. For the immediate, let's take a look at the immediate. So we have to have an immediate 8. Okay, only 8-bit. Only 8-bit. If you recall last time, I said we can have only 2 digits of hexadecimal for the immediate value. Why? Because in the format, we have only 8-bit as an immediate. So we cannot go any beyond that. And there's a ROT, rotation value. So only 8-bit is not enough to put large number of immediate. So anything larger than 256.
We have 1, 2, 4, 8, 16, 32, 64, 128, and then 256. With this 8 bits, 1, 1, 1, 1, 1, 1, 1, 1. So
255 is the largest that we can fit in as an immediate value. Anything greater than 255, so as I said, greater than or equal to 256, we have to use rotate. So we're going to rotate this to represent the higher number. We'll talk more about that. Let's do this. Copy this down. So let's do the first one. We'll go through this sequence. So opcode for data processing, what is it? 00. And that is 27 to 26 right there. That's the opcode. And then CMD. What is CMD for? Add 0100. So we have CMD. What is the value of I? 1. Why? Because I see immediate, right? Number 42. That's why we picked this guy. So I is 1. S, I don't see any S right after add. So it's going to be 0. And COND, we said everything is going to be 1110 in the data processing unit. Is unconditional. So it's not really applicable. So if it's not 1110, okay. And then RD, what's the value of RD? R0, so we cannot put R, I mean it's a register. R stands for the register, so we just take the number 0, so we need to put 0000 in the RD position, and then RN is 1, so 0001, and then rotate. We don't need it because it's less than 255, and put the 42 right there. So that's the complete 32-bit binary representation for add R0, R1, number 42. So the question is, what is I? What is S again? I is for immediate. So when you see this type of instructions, we have an immediate. And if you see R5, R6, R7, there's another possibility for the addition. Content of R6 plus content of R7, add them up, put it into R5, but I don't see any immediate. So in this case, we need to use I as a 0. We good? Okay. And the S, sometimes we have S at the end of instruction. That means subtract and set the flags. So what we do, R5 minus R7, we subtract it. If that is equal to 0, then the flags. We have 4 different flags: 0, negative, carry, overflow. So after you subtract these two, if it's a 0, set this to 1. If there is resulting negative number, n bit equals to 1. There is a carry happening, C equals to 1. S is overflow, V equals to 1. So that's the S. So if you see S at the end, this S value equals to 1. You don't see it, we don't have it, therefore S equals to 0. We got RD is the destination register. What is the RD value here? 5. What is the RD value here? 0. That's the destination. RN is the next one. And then after this, RM. It's going to be RM. That's our first instruction, going from assembly language to machine language. Now, once you get to this, I'm going to ask you to give me your answer as hexadecimal. Then you need to combine 4 bits at a time and then give me the answer. You take all of those numbers and form as a 4. Your answer should be OXE281002A. Let's take a look at this one. Add R5, R6, R7. Opcode again is 00, CMD add, so 0100. This time there is no immediate value, therefore I equals to 0, S equals to 0 because I don't see any S right after the instruction. COND conditional 1 is a 1110. And we know RD is 5 and RN is 6. We have RM as a R7, that's the 7, and the rest, there is no shift amount or shifting. We need to put just zeros, all of those. If we put that all into hex, this guy is going to be 0xe0865007. We got? So the next instruction, we could have something like this. We still see 3 registers, but after these 3, LSR logically shift left by 2 right there. Then that's the shift amount. So if we go through the same sequence, opcode is going to be 00, CMD is or 1100, and then immediate is going to be 0, set is 0, there's no S, and then COND is 1110, it's the data processing, and then RD is 9, RM is a 5, RM is a 3, and shift amount is going to be 2, number 2 right there. We have a 5 bits for the shift amount, and number 2, so you have a 00010. Yeah, why that's a 5 bit? So there's a reason for that. Why only we have a 2 bits? Because we have data processing, memory, and branch, 3. So in order to cover those 3, we need to have a 2 bits. And this condition is also, there's a number of conditions, so we can cover this 4. So we have to have a minimum number of bits, minimum number of bits, minimum number of bits for either I or not, either S or not, and then this CMD, when you look at all the number of instructions, 4 bits to cover all of those. Now for RN, RD, and RM, they are all registers, so which has to be 4, okay? 4, 4, 4. And then talk about this guy. We have 2-bit as more than enough, and we have 0 right there. I'll tell you more about that once we get to this. So we need that. And then all of these required minimum number of bits minus 32, 5. Good, good. The shift, so this is the shift type. Since we have 4 different ones, logically shift to left, logically shift to right, arithmetic shift to right, and rotate right. So those are the ones that we can use within the instructions, so we need only 2 bits. So now that's why it's a 0, 1. Logically shift to right is 0, 1. We put all of those binary number in here, and then combining 4 bits at a time, then we end up getting this hexadecimal number. Let's do this. Now we see R8, R9, R10, and rotate right, and R12. So register 1, 2, 3, 4. So we have to have this guy, register shift. Now shifting with the registers, not with the value shifting amount. So again, opcode 00, COMD is an XOR, so 0001, and no I, no S, condition 1110, RD 8, RN 9, RM 10, and RS, this 12, and then ROR was 11. Yeah. So if I test you, then I'll give you that. Any question? Yeah. For this guy, when you compare with this binary number versus this binary number, sometimes it's really hard. I mean, we'll talk more about it going from binary number to this instruction. So basically, these numbers will guide us which one is which. So that's the fixed number. This is, RM is back there, and if this is 1, now that is going to be this format, but in here we have a RM, but this time it's a 0, so 5th bit from the far right. Based on that number, we can identify either this guy or this guy. So that's the key. Good question.